Okay, let's talk about quantum mechanics. In that, our today's topic we will be talking about something known as, or not like we saw something new. It's the same thing, but we will just expand on how that this we will be talking about Planck's constant. Okay. Now, I think in first of all, before we Planck's constant, we know that Planck's constant is a fundamental constant in quantum mechanics, which is known as which is the symbol h, and it is also denoted as h bar, which is h over two pi. H bar and h, the only difference is that h bar is reduced Planck's constant and h is the normal one. For the reduced, we go for h over 2 pi. Now, the value for h is 6.625, oh sorry, 6 to 6 times 10 to the power minus 34 joules second. And for h bar, we know that it's divided by 2, so it will be 1.05 times 10 to the power minus 34 joules per second. Okay, that's the only difference, that the value changes. Other than that, they are both in the same field, quantum mechanics. They are important part of quantum mechanics. Now we know that this equation is like referred. Oh, sorry, referred for quantization of light, right? Now, if we change this equation, if we like write this equation the other way, which is E is equal to hv, it's not v, it's mu, it's nu, and it stands for frequency. Now let me explain what actually this equation is. This equation gives the energy, particularly for light. So it shows that a photon is better if I choose blue, so or yellow. Now this photon, now if it is coming down and it hits a metal surface, um let's talk, this is about photoelectric effect, but you don't have to talk like worry about it in this video, so I'll just give an overview. Now when this photon comes in and hits this electron over here, now for this electron to release, okay, for this electron to release, now it would require this photon to have a specific amount of energy, which and and the frequency of a certain frequency. So that's what the equation is about. This photon should have a certain amount of frequency, and that gives us a certain energy, of which if it's equal or greater than, sorry, greater than or equal to energy of electron bond in metal, it will escape. So that's what this equation is about. It gives us the energy of a photon traveling, a single photon. Well, if you multiply with the number of photons, because we know that at a single second many photons come out, but this is just to calculate energy of one photon. It can be used for yeah, for now let's just stay for the referred to as light, quantization of light. Also, one more thing, quantization means here it proves that energy is discrete, because we don't get all values, we get some values. Discrete, discreteness of light, or discreteness of particles in particular. Now uh, let's get to how we can use H in particular to get something known as Compton wavelength. Okay, which is the second form of photoelectric effect, which happens at when instead of here what happens that when this photon absorbs this electron, this electron absorbs the photon ceases to exist, means it vanishes to exist. But in Compton effect is this came from Compton effect. I have made a video on it. For the Compton effect, the special is what's special is that, pardon, is that um, in here photon doesn't vanish, it stays. It now we have angle involved, doesn't vanish. So let's not get into depth of Compton effect because that's not the purpose of our video today. So we'll be driving the Compton wavelength using h, Planck's constant. Now we know that E is equals to h mu, h frequency, and we can rearrange to get h is equals to E over frequency, right? Now I can also write it as E is equals to mc square over uh, 1 over second, which that is what frequency is, right? Now, what if I convert this into natural units? Okay, natural units. Now, we know that mass is represented by m. There's no change in mass. C or C is not, it's not C actually. It's uh, It's actually uh, it's actually d or d over t square. Now here d, which is distance, changes to is represented as L, length. These are natural units, and uh, t, it should be actually over here as well, t. Now this t is t is time, and it's represented as t as a whole. These are natural units. Okay, this can be written as m c over s negative 1. It's also the same thing writing as this. It's just I expanded the whole equation. Now, uh, let's shift this equation in using natural units. Let's shift them. So, how will we write it is, for m remains the same. H, we write them in blocks. M, let me make it capital, then written in capitals. Times, dot is the products, and d over t. D over t means L square. Don't forget the square for both, and t square over frequency, which is 1 over 1 doesn't change over t. And now when we simplify this t, this 1 over t is the same as saying t minus t to the power minus 1 if we bring t up. So I can write this, and this t can even be written at the can be written at the bottom. So it becomes m times L square over t. Now since it's t square and this t becomes negative, so it becomes t. So 2 minus 1 is equal to 1. Now this gives us our simplified version, which is this. Now this same equation, m times L square over t, can be written the same as taking L as a separate, one L separate, times m We have one extra L here because we took one outside, and T. Now you might look at if you might like have a familiar, um, you might feel like this equation is very familiar to one other equation, which is that first of all this part over here is momentum. Okay, now how is this momentum? This is momentum because L, we know that L is distance, T is time, and we know that distance over time makes velocity. So that means it's the expanded version of momentum equation. And this L over here is the radius, or it's like a distance. Okay, so this gives us. So if we rewrite the equation, we can get H is equals to uh, R, or let's suppose D times momentum, right? I can write it like this. I can also write it as H over D is equals to momentum. Oh, sorry, not we are going to we need the Compton effect, right? Compton wavelength. So we want this to be this to be down there. So over P, because D is meters, so it just gives us a Compton wavelength. Now, this equation is can be further expanded. Now, here, let's imagine we have the particle which has intrinsic spin, intrinsic spin. Okay, so here using this equation, intrinsic spin means it has a momentum, right? It has momentum. Now, which is angular momentum. Now, using this equation, we can say that uh, yeah, first, so not this equation, this is a Compton effect. This can be used over here. That if this particle which has an intrinsic spin, which is of course angular momentum, so this equation is nothing but angular momentum, which is d, which is the radius, like a certain amount of distance which is like moves, and p is the momentum. This is nothing but angular momentum. Momentum, which is used for this. So we can say we can define angular momentum for one half spin of a particle as one half of h, one half of Planck's constant. That's how we can describe um, one half spin particle. Okay, because we know that d is means a certain amount of distance traveled, and p is momentum, which in classical physics is angular momentum. So here it's angular momentum as well, which can help us define as one half spin particle, which is one half of a Planck's constant. Now this, okay, now let's talk about this equation by expanding it. Now let's add one more thing. Sorry, wait, let me make it accurate. Now let's say that this particle does have intrinsic spin, but it's not moving externally. Moving, no, externally, nully. Okay. Now, because no movement externally, we cannot put as v. So what we will do is that we'll put a c for the, which is a fundamental constant as well. So it becomes h over mc for momentum expenditure equal to d, and it's the same as writing as lambda is equal to h over mc. Now here, please note that this equation has nothing to do with, or it's totally separate from lambda is equal to h over mv, because in this equation the wavelength depends on momentum, right? But here, our only changing variable is mass. So here, our affecting or our independent or changing variable is changing quantity. Sorry, mass. Okay. Now that's what wavelength. So we can say that. So how will I explain this? I'll not go explain fully. I'll just give the overview of this equation. It shows that if we have an electron, let's suppose an electron, and by the way, it's the same for any electron. Now here, in this electron, which has rest mass m, and it is hit with a photon. I should have chosen yellow. It's hit with a photon, and by the way, this is a particle nature. We're talking about particle nature. Now, it's hit with a photon, but condition of same rest mass. Even we can say rest energy. Okay. Now, and that causes dispersion. Photon goes here. Sorry, electron goes here, photon goes here, and again it also depends on what angle you're shooting at. So I didn't talk about it briefly here, but you can check it out in the uh, Compton effect wavelength, because the angle also matters, at what angle the photon is coming, and using that angle you can have variation in variation in the dispersion, whether this photon goes back, goes down perpendicular, and I can write the equation for that, which is I can decide the equation. The wavelength is nothing. The scattering wavelength is wavelength or initial wavelength plus the Compton wavelength. Okay, and here Compton wavelength means the mass of the this guy over here, electron we're talking about, and multiplied by 1 minus cos. Wait, let me remove this, cos theta. So this is our equation for the Compton wavelength. Not Compton wavelength, the wavelength of the photon after scattering. And by the way, you might have noticed, yes, this value is a fixed value because h is a constant, c is a constant, and we all know that we know the mass of electron as well. So it's a constant, it's a non-changing value. Um, and theta and these two are the changing values. Now, is there something I'm missing? Yeah. So one last thing that I want to talk about here is that uh, I will remember I told you that this equation, which is the de Broglie equation, it's not it's known as de Broglie equation. Broglie equation. Now this de Broglie equation, I can drive this as well, but here we will have to involve two equations. E equals mc square, not mc square. E equals hv, and E equals to uh, momentum c. Now here you might have noticed that I don't have. Wait, let me fix it. Yeah, that's fine. Now you might wonder why I am wondering why I'm writing these symbols over here. Actually, this symbol stands for photon. That it's we're talking about photon because of photon having zero mass. Okay, not rest mass, zero mass when traveling at a certain speed. Now, because if I write E equals mc squared and P equals h pv mv, and if I divide it by 1 minus square root of 1 minus v over c squared, and same for here. Now this is a relativistic momentum and uh, momentum and uh, energy. But here we are talking about non-relativistic. Okay, I, yeah. So it becomes E is equals to hv is equals to E gamma, the gamma here as well, equals to hv Now this becomes, we can write this equation as this equation actually. We can write this equation as, we make P the subject here, which becomes E over C. Now replace this E with this equation and we get hv over C P lambda. Now you might now notice this. This part of the equation is nothing but uh, lambda equals to C over mu, sorry, frequency, and it's not the same, right? Now, what about this? 1 over lambda is equal to frequency over C. Now, does it match? Yes. So, something but the inverse of lambda. And so, we can write it as h over lambda. Hence, this is this predicts particle nature of light. As we don't have mass just we know that the mass of a photon is zero, so that's how we get this equation. And this is the de Broglie equation, the correct de Broglie equation, which is not the same as Compton wavelength equation, because Compton wavelength equation is fully dependent on the mass of the particle, whereas the Broglie equation depends on the momentum of the particle. And yeah, so this here is the derivation for the for the Compton wavelength using the natural units, using the Planck's constant, which also tells us about the spin particle. That if we talk about an intrinsic spin, what is it? What is an intrinsic spin? Intrinsic spin is a uh, what was it again? Yeah, intrinsic spin is the spin of a particle which is happening because of what it is and not what it is doing. That's one of the weird nature of particles in quantum mechanics. Because classically we know that spin is because of something, an object doing something, but it's not the same as in the no the other one, the quantum mechanics. And yeah, that's it. Thank you.